Hi everybody, this is David AtriSchuller from the MISSFIT collaboration at Drake University. This poster will be about the computational methods used in the MISSFIT collaboration, which stands for Magneto-ionization Spacecraft Shield for Interplanetary Travel. In essence, this is a large collaboration at Drake University led by undergraduate students whose aim is to solve the various challenges associated with prolonged interplanetary travel. Now, one of these challenges is the radiation exposure, since, as we know, interplanetary travel requires exposure to a large amount of radiation from various sources, and this poses a health risk to astronauts. Therefore, we aim to develop numerical and computational methods to simulate and arrive at viable solutions. Now, the solution we propose is to have a somewhat cylindrically shaped spacecraft with two spherically shaped gas bubbles at either end, and to have a magnetic field running along the spacecraft, which will either deflect incoming radiation particles away from the spacecraft, or if they are too high energy, guide them into the gas bubbles where they will interact with some gas via ionization and other processes, and thereby lose their energy and be neutralized and not pose a health hazard to the astronauts any longer. Now, in order to simulate this, we have two main codes. We have a magnetic code, which calculates the magnetic field, and we have a propagation code which calculates how particles move in this magnetic field and through the gas around the spacecraft. Now, the magnetic code, very briefly, we know that a magnetic field can be expressed as the curl of the vector potential A, and therefore if we take the Laplacian of A, the vector potential, and set it equal to 0, we're able to solve for the magnetic field given appropriate boundary conditions. So this is exactly what we do. We set up a grid and we give appropriate boundary conditions, and we relax iteratively until we have convergence of an accurate magnetic field. Now, this magnetic field is shipped off to the propagation code, which is a second order algorithm with respect to dt, and we're able to calculate the trajectory of many radiation particles, including electrons and protons and alpha particles, among others. Now we have a stable algorithm that once the particle reaches into the gas bubble, it will start losing energy since it will interact with the gas. So we use appropriate energy loss schemes from the literature, and this way we're able to calculate trajectories from various particles at various energies around the spacecraft. So let us consider some of the results briefly. Here we're scaling our magnetic field, which has a peak value of 16 Tesla at the planes where the bubbles stand in the z direction, and we see that higher energy particles, which are aimed directly at the bubble, do indeed penetrate and start losing energy at the bubble, whereas lower energy particles move away from the bubble and never reach it. We also check what happens if we shoot, or if we have incoming particles perpendicular and off-center from the spacecraft, and indeed we see in this case that none of the particles enter the spacecraft. The higher energy particles continue undisturbed, and the lower energy particles curl around the spacecraft but don't achieve any penetration into the spacecraft itself. We also compare three results for increasing magnetic strength. So here we have our same magnetic field just multiplied at every point. We multiply its magnitude by 0.1, so we scale down by a factor of 10, and we see that all particles travel unaffected by this magnetic field, meaning there's no curvature in their trajectories since the magnetic field is so small, until they hit the gas bubble, at which point they lose some of that energy, and then we start seeing some curvature in their trajectories. Similarly, if we use the magnetic field directly from the code, from the magnetic code, we see that the higher energy particles, which are depicted in red, go straight through, whereas the lower energy particles start curving. And again, we see that they must hit the bubble before we see any guidance of the trajectories by the magnetic field. Now, what happens if we increase the magnetic field and we scale by 1,000? Well, then we see that all the particles are completely deflected away from the spacecraft, and even the very high energy relativistic particles are completely deflected away from even the bubble, and they don't enter into the gas bubble. Now, from this, we're able to produced lots of runs, and we see here from a top-down view of 170 particles that only from very specific starting points and with very high energy they're able to penetrate into the spacecraft. Future work includes getting more higher order energy loss models, which include for angular straggling, for example, and to start running Monte Carlo methods to calculate statistics on penetration from different starting points, energies, angles for every particle. This work is funded by NASA and the Iowa Space Grant Consortium, and we also thank the founder and supervisor of the MISSFIT collaboration, Dr. Petridis. Thank you very much.